When we see the universe, we're seeing only about 0.0035% of what exists out there, meaning that the universe is mostly invisible to us because it emits light that our eyes can't detect. But what exactly do we mean by invisible universe? Well, light comes in many different forms, not just the invisible spectrum that our eyes can see. There's a whole electromagnetic spectrum out there. Let's start with radio waves. Picture them as the gentle giants of light. They have the longest wavelengths and can pass through thick clouds of gas and dust that block visible light. It's like having X-ray vision to see through walls. With radio waves, we can map the structure of our galaxy and even listen to signals from distant objects. One of our trusty tools here is the Very Large Array in New Mexico. These massive dishes are designed to catch radio waves from space. It's like standing in a field with a giant ear, listening to the whispers of the universe. Here's an example. Radio waves reveal the intricate spiral arms of galaxies and the activity at their cores, which are often hidden in visible light. Radio telescopes help us map out the structure of galaxies and even the cosmic web that connects them. They're also able to see pulsars and quasars, which are otherwise invisible. These telescopes also let us map the distribution of hydrogen, the most abundant element in the universe, showing us where new stars are forming, and can even listen for possible extraterrestrial signals. Next up, microwaves. These aren't just for heating your leftovers. In the cosmos, microwaves help us study the cosmic microwave background radiation, or the CMB radiation. This is the afterglow of the Big Bang, and it provides a snapshot of the universe when it was just 380,000 years old. Imagine being able to see a baby picture of the universe. That's what microwaves show us, revealing the universe when it was just a young infant. Studying the CMB helps us understand the origins and the large-scale structure of the universe. One of the most famous microwave detectors is the Wilkinson Microwave Anisotropy Probe, or WMAP, which has provided a detailed picture of this afterglow of the Big Bang. The CMB shows us tiny temperature fluctuations that correspond to the seeds of galaxies. Now, let's talk about infrared light, which is essentially heat. This light reveals objects that are too cool to emit visible light, but are still warm enough to glow in the infrared. Instruments like those on the Spitzer Space Telescope are like heat vision goggles. They detect the infrared light emitted by warm objects. This is especially useful for peering into dense clouds of gas and dust, where new stars and planetary systems are being born. Without infrared technology, these regions would remain hidden from us, like trying to see through a thick fog with regular glasses. Ultraviolet light is our next explorer's tool. It's more energetic than visible light and reveals some of the hottest and youngest stars. This type of light is also crucial for studying the chemical composition of distant galaxies and the interactions between them. It can also reveal regions of intense star formation and the effects of stellar winds and supernovae on their surroundings. The Hubble Space Telescope, while famous for its visible light images, also has instruments that detect ultraviolet light. And then we step into the realm of X-rays. When we observe the universe in X-rays, we see some of the most energetic and violent processes. X-rays reveal the hot gas in galaxy clusters, the remnants of supernovae, and the surroundings of black holes and neutron stars. The Chandra X-ray Observatory captures stunning images of these high-energy regions. These observations help us understand the extreme physics involved in these high-energy environments. Finally, we have the most energetic form of light, gamma rays. These rays expose the most energetic phenomena, such as gamma-ray bursts, which are the brightest events in the universe. These bursts occur when massive stars collapse and go supernova, or when neutron stars collide. Gamma rays also help us study the behavior of matter under extreme conditions and the interactions of cosmic rays with interstellar gas. The Fermi Gamma Ray Space Telescope helps us study these explosive events. Each of these technologies converts invisible light into images we can see. They're like translators, turning the universe's hidden messages into something we can understand. Without them, we'd be missing out on a huge part of the cosmic story. And when we combine all these lights, we get a richer, more complete picture of the cosmos, each wavelength revealing a piece of the grand puzzle that is our universe. Aside from the CMB radiation, one of the most important discoveries made possible by observing the invisible universe is the discovery of black holes. We can't see black holes directly because they don't emit any type of light, but we can observe their surroundings. One of the most groundbreaking achievements in astronomy was the first image of a black hole's event horizon, captured by the Event Horizon Telescope, EHT. This global network of radio telescopes worked together to create an image of the black hole at the center of the galaxy M87. This image of M87 shows the shadow of the black hole surrounded by a glowing ring of accreting material. It was a monumental moment in astronomy, providing visual evidence of black holes and confirming many theoretical predictions. And then we have exoplanets, or planets orbiting other stars. Scientists have discovered these worlds using various types of invisible light. Infrared observations, for example, can reveal the heat signatures of these distant worlds. Techniques like the transit method, which detects the slight dimming of a star as a planet passes in front of it, have been crucial in finding thousands of exoplanets. Infrared and other wavelengths help us not only find these distant worlds, but also study their atmospheres and compositions, opening up the possibility of discovering habitable planets. And then gamma-ray telescopes like Fermi have captured spectacular gamma-ray bursts, which occur during the collapse of massive stars or the collision of neutron stars. Another groundbreaking discovery is dark matter. While we can't see dark matter directly, we can observe its gravitational effects on visible matter. By studying how galaxies rotate and how light bends around massive objects, a phenomenon known as gravitational lensing, we can infer the presence of dark matter. Gravitational lensing, where the light from distant galaxies is bent by massive objects, provides clues about the distribution of dark matter in the universe, helping us map this invisible substance. One of the telescopes that have helped infer the presence of dark matter is the Chandra X-ray Observatory. Its observations of hot gas in galaxy clusters have helped scientists understand the mass distribution within clusters. By comparing the mass of the gas to the total mass inferred from gravitational effects, researchers can estimate the amount of dark matter present. The study of dark matter has shown that what we can see with our eyes and instruments is only a small part of the universe. Dark matter makes up about 27% of the universe, influencing the formation and behavior of galaxies. While we still don't know what dark matter is, observing its effects has been crucial for developing our current models of the universe. Each discovery answers and also raises new questions, driving our quest for knowledge ever forward. Don't forget to watch the video on the right and subscribe. Thanks for being part of Cosmoknowledge.